Hello Year 10, this is a special video for those of you that are unable to attend school at the moment. We didn't want you to be missing out, so we are going to be providing you with the same work that we are using with our Year 10 classes that are coming in currently during this time. So what I'm going to do is I'm going to lead you through the teacher-led examples. This would be the part of the lesson where we all work together as a class, and I would go through these questions with the students, maybe ask them a few questions, maybe give them an opportunity to demonstrate some understanding. So I hope you've managed to print out a copy of this sheet. The focus of this is to look at some 3D Pythagoras, and then later on you might find me doing some examples of some 3D trigonometry. So the first example that we're going to look at today is a cuboid. And we're going to look at how you could find some different lengths in a cuboid. Now, one strategy that I'm going to point out is really important, and I've popped it down here, is that sometimes visualizing these 3D shapes can be quite challenging, and sometimes drawing out some separate diagrams, 2D triangles, for example, can be really helpful just to try and visualize what's going on in the problem. And if it becomes a case that we need to do that, I will do that for some of these questions later on. Okay, so here we have a cuboid, A, B, C, D, E, F, G, H. We have some measurements for the cuboid, and the first thing that we are going to try and do is find the length FH. Now you can see, looking down on this shape, that FH is the line segment that joins F to H. If you were looking straight down from above, this is the triangle that you might be able to see. This triangle that I'm drawing isn't this dotted triangle, it is this triangle here. It is F, E, H. It's a really bad E, but I'll make it better. There we go. So that would be looking straight down on this shape. And with some of those lengths we already know. We know E to H is 4 centimetres. And we know that FE is 3 centimetres. And we've been asked to work out F to H. Now, of course, I'm going to assume that you know how to do Pythagoras' theorem here. If you're unable to remember how to do Pythagoras' theorem, then I'll perhaps put a link in the video description below to a Corbett Maths video on Pythagoras. Okay, so we know that for Pythagoras that a squared plus b squared equals c squared. So I know that my x is my hypotenuse. So 3 squared plus 4 squared equals x squared. Remember, I'm trying to work out what x is. 3 squared is 9. 4 squared is 16. And that equals x squared. 9 add 16 equals 25. So x squared is 25. To work out x, I have to do the square root of 25. And the square root of 25 is 5 centimetres. Now, maybe one or two of you would have actually said, oh yeah, I know that x is 5 straight away, sir, because this is one of those special, what we call Pythagorean triple triangles, where we know there's a relationship between those numbers, and a 3, 4, 5 triangle is a very special case. Okay, we're now asked to find the length of BH, and this is why I've got this dashed triangle already drawn in. We already know that FH is 5. And we know this vertical length is the same as this one, so it is 3. So I am now working out B to H. So I'm looking at this triangle here, and that, although it wouldn't look like it, is actually a right angle. So for this question, I need to do that. BH squared. So BH squared just means the length of BH is, again, it's the long side, 3 squared plus 5 squared. 3 squared is 9. 5 squared, 25. So that equals 34. So if I want to work the exact length of BH, it would be the square root of 34. Now you could leave it like that if you were trying to work out an exact length. Okay, that you might recall is called a surd, and the square root of 34 doesn't simplify. But if we wanted an exact answer, or an answer to a decimal place, I could write this as to 2 decimals 5.83. And that would be to 2 decimal places. Now, in this box here, I have talked about a little shortcut for how to find the length of an opposite diagonal in a cuboid. It's basically an extension of Pythagoras' theorem, and this diagonal can sometimes be referred to as a space diagonal. And the formula is that if you want to find the length of this diagonal squared, you square and add together all of the lengths of the 3 sides of the cuboid. So again, I've just quickly shown you here that doing it this way for the diagonal BH gets you straight to the square root of 34. So for a cuboid, that is something that you might consider as a possible shortcut if you are going straight to the length of some opposite diagonals. Okay, let's move on to a slightly more difficult shape, but there are some questions like that for you to try if you choose to do so. And another very typical shape that you might be asked to look at is a square-based pyramid. And I'm going to break this one down into 3 questions. Okay, so here's a picture of my shape. If you're interested, point O is directly below X, and you can think of point O is exactly in the middle of that square base. So I've told you it's a square-based pyramid, so one thing that we do know is if this side is 10, this side would also be 10. And the first thing that we've been asked to do is find the length of AC. And again, looking down from above, we've got a right angle triangle there. AC, B. This angle has to be a right angle because it's a square base. And we've got lengths of 10 and 10. So if I want to work out the length of AC, AC squared would be 10 squared plus 10 squared. Again, I'm finding the longest side here. I think we can rattle through this one quite quickly. 10 squared is 100, 10 squared is 100. So all of that is 200. But of course, if I want the length of AC, I need to do the square root of 200. Now, there's a couple of opportunities here. If you were asked to do this as a surd, you could simplify that surd, and I'll just quickly do that for those people that understand what I mean by simplifying a surd. It's the square root of 100 times the square root of 2. Remember, when you simplify a surd, you're looking for a square number factor. So I could write it as 10 root 2, or if you prefer using decimals, square root of 200 is 14.14 to 2 decimal places. Okay, so that would be finding length AC. Next thing that we've been asked to do is find the length of OC. So that we've just worked out AC, and now we're working out OC. Well, I'd hope you notice that OC is just half the length of AC. So if we know it is 10 root 2, I'll do it as a surd if you want first. We just need to divide that by 2. And if you had 10 root 2s and you divide it by 2, you'd be left with 5 root 2s. Or, if you prefer it as a decimal, it's half of 14.14. And that is 7.07. Okay? So, or 7.07 centimetres to 2 decimal places. Okay, so entirely up to you if you want to use this as an opportunity to practice some thirds as well, or whether you just want to work with decimals. You'll find in all the answers that I've provided, I've tried to do a mix of both for those students that want to do it either way. Okay, finally, our last question is work out the length of OX. And I'm going to draw another triangle here. The triangle I'm going to draw is XOC. So XOC. There's some numbers that we already know. We already know that the length of XC is 13. And we already know that the length of OC is this number here, 5 root 2, or 7.07. I'll write 7.07 ... And the reason why I'm going to write it as ... because I know it wasn't 7.07 exactly. It was this lovely number, if you remember. And always where possible, if you can, try not to round too early if you want to maintain accuracy in your final answers. The exam boards are pretty generous when it comes to exam questions about whether you've rounded a little bit early, but I always like to be as accurate as I can. So let's see if we can work out the length of OX. Now, one thing that you'll immediately notice is this is the shorter side, or one of the shorter sides of this right angle triangle. And that's super important because that means that if we are finding a shorter side, we are going to be subtracting when we square those numbers. So I need to do the hypotenuse squared, 13 squared, times this number, 5 root 2, or 7.07 squared. And this is the reason why I've left this on the calculator. It means I don't have to type it in again. Because what I can see is if I square that number, it actually ends up as a really nice number. If I'd squared 7.07, there's my little bit of inaccuracy. Okay, not going to make a huge difference, but I like to be exact. So, 13 squared I know is 169, and that, I just showed you on the calculator, was equivalent to 50. So OX squared is 169, take away 50, which is 119. So if I want to find OX, it is the square root of 119. Don't think that simplifies as a third, so you'd have to leave it as that. Or if you wanted it as a decimal, 2 decimal places is 10.91 centimetres. So, there we go. There are some questions for you to try, some other activities for you to do. There's more than an hour's work, or if you are looking at both lessons at the same time, we've approximated this should be about 100 minutes. There is far more content than you should be able to do. So pick and choose the questions. I've tried to differentiate the tasks so you could jump in at different points depending on which set you belong to. But for the time being, that's going to be me signing out. If you want to get in touch, probably best email me because I know the resources the most. So this is Mr. Butterworth. Just drop me an email and I'll do whatever it is I can to help. Take care, folks. Signing out and goodbye.